Aloha again, this is Rob Kelso, Executive Director for the Pacific International Space Center for Exploration Systems, PISCES, in Hawaii. We're a state-funded program doing planetary research and development for surface systems in Hawaii. And I'm here to talk with you today about planetary basalt construction. Within the portfolio of tasks that we do for the state of Hawaii, we look at planetary rover systems, managing and operating, defining analog test sites to include skylights and lava tubes and surfaces that are almost exactly like Moon and Mars and basalt. We have a lunar flight program called Moon Riders. We're also involved with NASA in some laser communications. But we also were involved, given the very close nature of the chemistry and morphology of the basalt in Hawaii compared to Moon and Mars, efforts involving basalt construction and 3D fabrication. So on the fabrication piece, I don't have a slide on that, but we are doing 3D printing with high-powered lasers in our lab. The goal being to do 3D printing of parts for surface systems like a rover, but not made out of ABS plastic or plaster of Paris, but made out of basalt. Because when you get to the Moon and Mars and you have to do fabrication or construction, you don't want to take a lot of supplies with you. You want to live off the land. That's called in-situ resource utilization, or ISRU. So you're using the materials that are there on the Moon or there on Mars. So we're looking at how we can use fine-grained materials of basalts as feedstock for doing 3D printing of three-dimensional parts. As a part of that, we're also looking at it from a construction standpoint. And we have two projects that we are involved in. One that we just completed mid-March here in downtown Hilo, which is on the east coast of the Big Island of Hawaii. And that's what we call a lunar sidewalk or sustainable concrete. It's interesting that the state of Hawaii now imports 300,000 tons of Portland cement a year to load sidewalks, foundations, construction material. And so what we're looking at is how we could use not concrete to do construction on Moon and Mars, but the volcanic basalt material on Moon and Mars to do construction. And out of that, perhaps there's dual-use technology where the state of Hawaii in and of itself could begin to lessen the import of concrete into the state by using more indigenous material, and in this case, basalt. So one of the things we want to look at is doing a sidewalk construction, not with concrete, but with basalt. The slide here is the old sidewalk before construction, where it was cracked and formed. And we entered into partnership with the Department of Public Safety, Department of Public Works in the county, and NASA, the University of Hawaii at Manoa, Civil Engineering Group, and PISCES, and looking at various ways to put basalt sidewalks in place of concrete with various binding agents. And here you see just a couple of weeks ago, third week of March, we began the construction of that sidewalk with different elements. One is very fine-grained basalt particles that come out of quarry that are at 150 microns or below. And the University of Hawaii Manoa used fly ash as a binding agent, and then they mix it into a concrete mixer and then pour that. So two of the pads used this basalt fines plus the fly ash binder. One of the pads had a basalt rebar that I'll talk more about. The other pad did not. So we're going to look and see how the sidewalk holds up and operates over a year, one with basalt rebar, the other one without. The one in the middle where you see little black plates are actually baked basalt from an oven that uses X38 tiles at NASA Kennedy. They took those high temperature reentry tiles that have been planned for the X38 vehicle, and built a high-temperature oven, and then took our fine-grained basalt powder from the Big Island and then melted that into the sintered blocks. And then they shipped those blocks to us, and we put 20 of these blocks down in the sidewalk, again, to evaluate how basalt as a construction material would operate over a year. So we're looking, do they crack? Do they deform? How do they wear and tear over a year? We'll be taking samples out periodically to do compressibility testing, tensile strength testing, etc., volumetric loss over the course of the year. Here the fine basalt and the fly ash is being flowed over the basalt rebar that you see in the crosshatch lattice structure here in the sidewalk. This is being performed by a PhD manager from UH Manoa plus 2 grad students. And this shows the final emplacement of those basalt pads that came from NASA Kennedy as a third element, sidewalk paver within the county here. So let me go back to this idea of basalt rebar. Right now, traditionally, civil engineering uses steel and iron rebar. A lot of that is often imported from like China. And steel and iron rebar rusts, especially if you're in places like Hawaii or in Florida where you get the salt leaching. The salt gets in there and weakens and expands the iron or steel to the point where it fatigues and rusts and it has to be renewed. Unlike steel and iron rebar, the basalt rebar is lighter in weight, it is stronger, and does not rust. And so it could prove to be very interesting construction material as a substitute for steel and iron rebar for certain industries, for sidewalks, for bridges, for roads, for piers. We think pretty much for a lot of things except for load-bearing walls. And this plays very well in Washington at Congress when I talked with them about that, because it plays within the sustainability initiative in the state of the state wanting to become more self-sufficient, less dependent on 2,400 miles to the mainland of the United States. And if we're able to generate and develop and construct basalt rebar here in Hawaii, we could significantly lessen the amount of steel and iron rebar that we import into the state from China for civil engineering construction. It also plays well in the American Competes Act, where you look for where America can compete in high-tech industries as opposed to currently established markets and industries in the international sector. And so it also, there's a new initiative in Hawaii through the Hawaii Technology Development Corporation, HTDC, called 8080, where they want to create 80,000 high-tech jobs paying $80,000 or more by the year 2030. So one of the things we're looking at here is, of course, if we do construction on Moon and Mars, we don't want to ship and launch steel and iron rebar from Earth. That's too expensive, too heavy. So we have to make the rebar out of basalt on the Moon and Mars. So we're also looking at there's a new 21st century industry for Hawaii and other mid-Pacific islands like Iwo Jima and others that are volcanic-based for using basalt rebar as a substitute for steel and iron rebar, and in a sense creating a new industry not only just for Moon and Mars, but for the Pacific Rim. Another project that we are doing is out of the Space Technology Mission Directorate. Mike Gazarek, the former director of STMB at NASA headquarters, had contacted PISCES about serving as a strategic partner in additive construction using basalt materials in a project called ACME. And this project involves the Kennedy Space Center and PISCES in the first of a three-phase, 3-year effort The first year is to build essentially a two-dimensional launch and landing pad out of basalt. The second year is to make curved walls through an industrial print head, but not with concrete, but rather using basalt material. And the third year would be able to make a domed or an enclosed structure, as you might find on Moon or Mars, for protecting high-value equipment like rovers and other things. But the first year is to build a launch and landing pad using a robot. So PISCES is involved in beginning this operation using our large 700-pound planetary rover with a back blade on there to do back blading to smooth the surface of the basalt, and then come behind that and stabilize it with various technologies. So the first phase of that would be for us to develop a test arena with basalt materials in it that we can perform robotic backblading operations, early grading operations. And then in parallel, we're looking at various technologies for stabilizing and sintering the surface, to include induction furnaces, microwaves, solar, polymer binders, etc. And also, how do we, if we develop pavers like we used on the sidewalk, how would a rover drop those down? Pooping bricks, if you will. So how does a rover lay out these pavers? And so we think we're also going to need some type of end effector or actuator to help move and interlock pavers together as a part of robotically building a launch and landing pad. Our intention with NASA Kennedy then is to lay down this launch and landing pad robotically in the July-August time frame, and then to run verification testing of the landing pad with some simple load tests and maybe some of the high-velocity gas expulsion tests using our system that we recently used for the Moonriders test program to disturb dust up at the test site, and use that as a simulated thruster in evaluating the effects of thruster plumes on the stabilized and centered launch and landing pad that we built. So our intention is to maybe make a bullseye of the landing pad with centered brick pavers out of basalt in the center core of the bullseye, about 10 feet by 10 feet, laid down by the PISCES robotic rover, planetary rover. And then the outer ring, the outer apron of the landing pad would then be stabilized or centered with a polymer binder, essentially a liquid polymer that would flow out through various veins, spray nozzles at the back end of the rover to help stabilize the surface. One of the reasons we're doing this is that we found back in looking at Curiosity data and the Apollo lunar landing data that the descent and even ascent of lander vehicles on Mars and Moon create extremely high velocity dust particles. And unlike the billowing of dust that we see here on Earth with the atmosphere, on the Moon they get into high density sheets of particles about a degree or two off the surface. And these small micron particles can get up to 2,000 meters per second. So if you think of a sandblaster maybe at 300 meters a second, we could easily sandblast away and totally destroy outposts and other high-value hardware if that hardware were in line of sight to these landers that would repetitively launch and land near an outpost. And so centering or stabilizing the surface to minimize the blowing dust interaction off of high thrust rocket engines is paramount to building infrastructures and settlements on Moon and Mars. And so that is the goal of this first year at a NASA headquarters, with us building a basalt launch and landing pad on the Moon. So with that, I thank you for allowing me to come and share today some of the incredible technology development that is being applied for basalt construction. not only for Moon and Mars development, but also application technologies that can have benefit to the state of Hawaii as well. Thanks for letting me come and share with you today.